Welcome to Lecture 14. In this lecture, we're going to use Gauss's law to find the electric fields around different objects with different kinds of symmetry. For this example, let's use Gauss's law to find the electric field due to a spherical conductor carrying a net charge Q, and our conductor has radius A. So the radius is A here. First, before we begin, let's collect our thoughts and get all of our tools at our fingertips. First question is, what is the nature of a conductor? What makes a conductor a conductor? Well, what's special about a conductor is that the charges are free to move. Because they're free to move, they spread to the surface. And we've discussed this already, but let's just do a reminder as we begin. So they spread to surface. If we know the charges spread to the surface, let's just go ahead and draw some charges at the surface. So they're right on the very surface of the conductor. So whatever charge is in this net conductor is on this conductor, all of it is at the surface. Next, we know we're going to apply Gauss's law. So for our next step, let's write down Gauss's law and let's make sure we remember what it is we're talking about. The electric field integrated over the area of a Gaussian surface is equal to the net charge enclosed by that Gaussian surface divided by the permittivity of free space epsilon naught. So we're doing an electric field over an area, in particular the area of a Gaussian surface. That means for our next step we need to pick a Gaussian surface. When we pick a Gaussian surface, there are two things to keep in mind. It should match the symmetry. Our charge, our conductor, is spherical. So for our Gaussian surface, let's pick a sphere. And our sphere will have radius r. And I'm not exactly sure how to phrase this, but let's just say have it to be useful, where we want to find the field. So be useful. Let's start. We want to find the electric field inside the conductor and outside. Let's start with inside. So to be useful, let's pick the radius of our Gaussian sphere, Gaussian surface, to be less than the radius of our conducting sphere. So we want our Gaussian surface inside because we want the electric field inside. That's useful. Okay, after we choose our Gaussian surface, next we draw it. Of course, I'll draw a two-dimensional projection. So our Gaussian surface is just a sphere that we draw inside our conducting sphere. Let's put the radius on there. There's our radius r. All right, now we've got a picture of what we're doing. We've got our Gauss's law. Next, we need to apply Gauss's law and calculate the electric field. As a hint, you probably already know what the field is because we've already discussed this result previously. So let's start by writing down our Gauss's law again. E dot dA equals Q enclosed over epsilon naught. Now, one of the pitfalls for a lot of students is sorting out what is Q enclosed. Let's remember what Q enclosed stands for. So Q enclosed is the net charge inside the Gaussian surface. Loads of people find this a little bit tangly to figure out, so take your time. I suggest you pause here and ask yourself, do you know what the charge enclosed is? And then unpause and just make sure, double check what the answer is. So Q enclosed is the net charge inside the Gaussian surface. So how much charge is inside this circle I drew? Let's remember, we represented the charge by a bunch of plus signs. We drew all those pluses on the surface because we know the charge is on the surface. So if the charge, all of our plus signs are on the surface, can there be any charge inside? I would have to say no, there can't be any charge at all inside. So our Q enclosed must be 0 because all of the charge is gone to the surface. So next step in our equation is to write that the integral of E dot dA equals 0. If the integral of E dot dA is 0, that means that the electric field is equal to 0. Okay, there's a result we were anticipating because we know the electric field inside a conductor in electrostatic equilibrium is equal to 0. This part's not surprising. Next, we'll move on to the electric field outside the conductor. We'll follow the same steps now to find the electric field outside of our spherical conductor. We'll remember that all of the excess charge is on the surface of the conductor, so I already drew in those little plus signs. Next, we write down Gauss's law. It says that the integral of E dot dA is equal to Q enclosed divided by epsilon naught. This means that we're doing the integral of electric field over a Gaussian surface with area A. That's equal to the net charge enclosed by the surface divided by the permittivity of free space epsilon naught. Next, we have to choose a Gaussian surface. Remember, we want to choose our Gaussian surface so it matches the symmetry. So we're going to pick a sphere. We want it to be useful, so we want to draw it at a place where we're trying to calculate the electric field. So let's choose our sphere to have a radius greater than the radius of the sphere. And after we choose it, let's draw it. So that's the next step in our problem. I can't super well draw a sphere. Imagine that this crazy shaky dotted line is actually a spherical surface. We'll label it as having a radius r. Of course, I'm doing the two-dimensional drawing. I don't want to try and draw a three-dimensional sphere. So now the next steps in our process is let's figure out what is Q enclosed and how are we going to do this integral E dot dA. So those are our next two parts. Let's figure out the left-hand side of the equation and the right-hand side of the equation. So let's start with Q enclosed. So Q enclosed, remember this is the net charge enclosed by the Gaussian surface. Our Gaussian surface is out here. How much charge, how many plus signs are inside this circle? So hit pause here and write it down, then unpause and see if you got the right answer. I would say that inside this circle, we have all of the plus signs. None of those charges are outside the circle, they're all inside. So our Q enclosed is the net charge on the conducting sphere Q. Okay, half of our equation is dealt with. We know what Q enclosed is. Next, let's go on to the left-hand side of the equation. Let's get working on that one. So the integral of E dot dA, let's deal with the scalar product part first. That's the integral of the magnitude of the electric field times the magnitude of an area element. We're going to discuss that in just a moment, times the cosine of the angle between them. Okay, here's a good time for a refresher about area, and we'll also draw our electric field. Since our charge is positive, our electric field is going to come straight out from the surface of our conductor. This is a result we're going to prove. So if you wish, you can skip ahead to where we prove that result, or for the moment, you can just accept. So outwards because it's positive and it's perpendicular to the surface of the conductor. So this is what our electric field vector looks like everywhere. So remember, outwards perpendicular to the conductor. There's the electric field. An area element dA is just a little bit of the area of our Gaussian surface. That's what dA stands for. It's a little bit of the Gaussian surface. So here we have to remember what the direction of an area vector is, and the direction of an area vector is straight out from the surface. So let's draw that guy. So there's our area element, dA. The area element points straight out, the electric field points straight out. Those two vectors are parallel. That tells us that theta equals 0 because our electric field is parallel to our area vector and our area element. This is why when we pick our Gaussian surfaces, we always use that symmetry because we get things to be parallel, and we'll see some examples, we also get some perpendicular, but it means it allows us to deal with the integral. If we had something odd here, we wouldn't be able to evaluate this. Okay, let's move on to the next step. We've got the integral of E dot dA times the cosine of 0. Cosine of 0 degrees is just 1, so we've got the integral of E times dA. E refers to the magnitude of the electric field at this Gaussian surface. So at this surface right here, this is where we're finding the electric field. Our surface is at a constant distance r, so our electric field will be constant everywhere we're at that same distance r. So our electric field can come out front of the integral. So we've got E outside of the integral of dA. E is constant at a single distance. So that's E. The integral of dA is just A. A refers to the area of the Gaussian surface. Maybe that's worthy of a note. Our Gaussian surface is a sphere with radius r, so the area of a sphere with radius r is 4 pi r squared. Oh, little heads up here. Sometimes people get area and volume mixed up and they might pop in 4/3 pi r cubed, but that's volume. A stands for area and the area of a sphere is 4 pi r squared. Okay, looks like we're ready to put it all together. We'll put in E times 4 pi r squared for our integral part. We'll put in Q for our Q enclosed, and we should be able to solve for our electric field vector. Okay, let's put it all together. So we started with Gauss's law, the integral of E dot dA equals Q enclosed over epsilon naught. We sorted out that the integral of E dot dA was E times 4 times pi r squared. We figured out that our Q enclosed was the net charge Q. Don't forget to divide by epsilon naught. Now we'll solve for the magnitude of the electric field. It's going to be 1 over 4 pi epsilon naught times Q over, Q over, I wrote epsilon, I should have wrote r squared. Electric field is a vector, of course, and the direction of the electric field is radially outwards because it's a positive charge. Had it been a negative charge, it would be radially inwards. If you see this result and you see 1 over 4 pi epsilon naught, you might recognize that that's our Coulomb's constant K. So you could equivalently write E is equal to K times Q over r squared outwards. The interesting thing about this expression is this one might ring a bell. When we have a spherical conducting charge, the electric field on the inside is 0, but outside it's kq over r squared. It's just like a point charge. So the electric field outside of our spherical conductor looks just like a point charge. That's kind of an interesting result. Now, physicists graph just about everything, so let's summarize our results and let's make a graph of the electric field as a function of distance from the center. We'll remember that inside, the electric field was equal to 0, and outside, the electric field was equal to K times Q over R squared. An interesting point that we'll want to think about is what happens when our distance is equal to the radius of the sphere, which we labeled as A. So inside, the electric field is equal to 0. Draw that with a blue line. When we get to the surface, that's kind of an interesting point. So let's switch colors here. At R equals A, the electric field is equal to K times Q over R squared, but R is equal to A. So that gives us a point to put on our graph. So let's go back to our graph. Once we're outside, the graph starts here at KQ over A squared. We see that the graph goes as 1 over R squared. So as R gets bigger, E gets smaller. So it falls off. Something like this. And then we can label the interesting spots on the graph. So at R equals A, the radius of the sphere, E equals KQ over A squared. This is a maximum value that the electric field is going to have. At R gets really big, E goes to 0. So as we get infinitely far away from any charged object, the electric field gets small. In the middle, the electric field falls off as 1 over R squared. So this is all outside. And then on the inside, we have that our electric field is equal to 0 until it gets to the surface.